over a field K, which is algebraically closed, and we're especially interested in the case where the characteristic of this field is positive. So the standard example, of course, could be GLN. You can think of this as GLN over this field K. So we are interested in representations of this group. We want to classify our representations of this group, and the situation we consider now will be that the representations are the same. In this case, they are called rational representations. So a rational representation is just a K vector space V and a homomorphism rho of G to GLV of algebraic groups. So this should be both a homomorphism of groups and a morphism of varieties. So this special situation in representation theory is kind of a mixture of group theory and algebraic geometry. So to give you an idea of what is happening, we'll look at the case of GL2. Let me give you the main example. If G is GL2, well, this group comes with an obvious natural representation. I mean, the embedding or the identity of GL2 in GL2. So it has a natural two-dimensional representation. You can take tensor products of this two-dimensional representation to create a lot of other representations. And in this case, you end up, if you look at the tensor algebra of this space, you end up with representations on the ring of two variables, kx, y, and it acts as follows. So a matrix A, B, C, D acts on a monomial of the form x to the I, y to the j in the following form. Well, you think of x as being the first standard basis vector, y the second standard basis vector, and then you look at the linear representation of these matrices on x and y, and so this will be ax plus c y to the I, and bx plus dy to the j. This, of course, is a representation in an infinite dimensional space, but you see that the total degree of these polynomials is preserved, and that means that if you look at the subvector space inside this algebra of homogeneous polynomials of total degree n, and then this is preserved. It's an n plus one dimensional representation. So this is n plus one dimensional, and it's action. You see that this action is given by polynomials. So to understand this action, you relate these expressions, and you get long expressions, polynomials in A, B, C, D in front of these homogeneous monomials, and you can kind of, by waving your hand a little, you can see that this is an irreducible representation, so it doesn't have a non-trivial subrepresentation in case the characteristic of your ground field is 0. So if the characteristic of the ground field is 0, then this is actually irreducible. And in this case, we call it L of n. So that is the definition. But in positive characteristic, there is this, basic phenomenon of the Frobenius morphism, namely x to the p and y to the p span an irreducible subrepresentation. So this is in k, x, y, p is a subrepresentation. Well, just because, you know, if you look at this formula, so ax, so if you, for example, apply a, b, c, d to x to the p, y to the 0, then following this formula, you have ax plus by to the p, and the pth power is an algebra homomorphism. So this is a to the p, x to the p, plus b to the p, y to the p. And you see x to the p and plus y to the p, so these span an irreducible subrepresentation, and in this case, this is called L of p. So that's a general phenomenon in characteristic p, a phenomenon with which we have to deal. So going back to the general case, so this gives you an idea of what happens in characteristic p. And in a general case, so this can be generalized. So the role of kxy to the n is played by global sections of line bundles on Fleck varieties. So these spaces should be considered as the space of global sections of a line bundle on the Fleck variety of GL2. The Fleck variety of GL2 is P1, and you see the global sections of all twisted line bundles on P1 appearing here, and GL2 acts on P1, so it acts on these global sections, and so this creates all these spaces, but they don't need to be irreducible. So in general, you define the Weil module, or maybe one should call it the dual Weil module rather. So H0 lambda, this is global sections of a line bundle. Let's call it L lambda on the Fleck variety of G. So here lambda is a character of a Borel subgroup, or it's considered as the characters of a maximal torus. So in order to define this, we choose a torus inside the Borel subgroup inside G, a maximal torus, and a Borel subgroup. And then the Fleck variety is G modulo B, and so the characters of the torus yield line bundles on G mod B, and so the characters of the torus are just the homomorphisms of algebraic groups from T to K bar, and this is so this is a space that originates geometrically in this theory, and you can prove, there's a general fact that so this is a G module, a representation of G. H0 lambda contains a unique irreducible submodule, and this we call L lambda, and this set of L lambdas is a okay. Well, sorry, there's one condition. So I mean, it could be that H0 there are no non-trivial global sections. You see that already on P1, of course. So this is the case if lambda satisfies some kind of positivity constraint, so if lambda is inside the dominant weights, the set of dominant weights. And in this case, you have this irreducible submodule L lambda, and this is a complete set of representatives of the irreducible isomorphism classes of rational G representations. So it's a complete set of irreducibles. So, and these statements are not super hard to prove, and they are quite remarkable because this X plus, so X is a lattice. So you have algebraic homomorphism of algebraic groups from a torus. A torus is just product of copies of K cross to K cross. This is a lattice, so it's isomorphic to Z to the R. Integers to the R is an abelian group, and so you inside there you have this dominant Weyl chamber, dominant cone, and it's independent of the ground field K. So there's a kind of discrete set underlying the theory that is independent of the ground field K. But as we have already seen for GL2, the structure of these L lambda heavily depends on the choice of the ground field. And unfortunately, there is no direct way to realize L lambda as global sections of something on the Fleck variety. So we don't have a direct geometric approach to these L lambdas. And today, there's a lot of things that we don't know about these L lambdas. For example, we don't know their dimension in all cases. So the major problem in representation theory very often is to describe these irreducible representations, and a description of these irreducible representations amounts to determining, for example, the dimension. But there's an invariant that is even more important. It's finer than the dimension. It's called the character of such a representation. So the character of such a representation is the following. So T, this maximal torus, so we call it isomorphic to the multiplicative group of your ground field to the R. So this is a group we have chosen from the beginning inside G. It has some maximality property. So this acts semi-simply on each rational representation, which is a remarkable fact, a very nice, very important fact. So that means that a lambda splits up into irreducible, into a direct sum of irreducible representations of the torus, and these are all one-dimensional. So it decomposes into a direct sum, so canonically into a direct sum of its so-called weight spaces. So mu is again an element in this set X, and this is the eigenspace of the T action with eigenvalue mu. So that means this is the space of all M, such that an element of this torus T acts on M just by multiplication with the scalar mu of T. Okay, this is the weight space decomposition of this module, and then you define the character of L lambda just as the formal sum of all the dimensions of these so these are k vector spaces. You calculate the dimension, and then you form this kind of sum, and you consider this as sitting inside the group ring of this abelian group X. So the problem that modular representation theorists have to solve is to determine this character. For example, I mean, you get the dimension of the whole space if you just replace this by 1 and just take the sum. So it's a finite invariant. It's a very important invariant because these characters determine the simple representation. So there's, if you have two simple representations having the same character, then they are isomorphic. It's not true in general that two representations having the same character are isomorphic. So what the character doesn't see is kind of extensions of simples. So not every representation of G splits into a direct sum of irreducible representations of G. It's true in characteristic 0, it's false in characteristic P, as you can see already here. This is a KXYP is a non-irreducible but non-decomposable, indecomposable representation. So, character of a lambda. This is what we want to know, and people studied that a lot. And so one of the most important facts in representation theory is that it's actually enough, once you fix your group, it's actually enough to calculate this character in finitely many cases. So X plus, the problem, let me just write it down, is to calculate this character for all dominant weights, and this is an infinite set. But you can reduce it to a finite subset using several results. So Janssen's translation functors are very important there, and also Steinberg's tensor product theorem. So the next fact in representation theory is that it's enough to calculate this for restricted representations. It's enough to know the character of L lambda for restricted lambda, and that means the following. So if you, if you know there's a root system kind of as a combinatorial base of the whole theory, let me just write it down. Lambda evaluated at a root alpha check should be positive. That is the dominance condition, but it should be smaller than P for all simple roots alpha. So this is a condition which comes from the underlying root system of the group. Anyway, there's only finitely many lambda that are restricted. And in this case, Lustig has a conjecture. So I won't. So this conjecture is a little bit technical. There will be a lot of things appearing that I don't really want to define, because it's really a technical thing. But let me just write it down so that you have seen that the character of W dot lambda should be given as a formal sum. Not a formula, as a sum over certain x. It's an alternating sum. There's a sign, and then there's the so-called Weil character. So that is the following expression. So that's the so-called Weil character. It is, in fact, the character of H0 of x dot lambda. You see it of these global sections of the line bundle, and this is There's the Weil character formula that gives this character. So this is a formal, an alternating sum of known characters, and there's a certain weight, and it's W0x, W0w, evaluated at 1, and this h here is a polynomial in one variable, v, and it's called a Kashtan-Lustig polynomial. So this is Lustig's character formula. I mean?
That chi-x lambda also is included in the formula. Yes. Yeah. Okay.
He's asking whether the character of the volume.
Right. So this is.
Yes, it's part of it.
The formula is 3 terms. Okay. X of this 2 terms.
What is the summation over again?
Yeah. So this is the summation over x in the affine Y group, where x dot lambda is restricted and dominant. Restricted and dominant. So this is an explicit formula. Everything is known there. And so this should give the character of this w dot lambda. So w is another element of the affine Y group, and lambda should be such that so lambda should be such that 0 is smaller or equal to lambda, beta check smaller or equal to p for all positive roots. But then reflecting it with an affine Y group element gives all restricted elements. So this is just to formulate this conjecture. And suppose the formula. So Lustig said that he didn't claim that this formula is correct in all cases. He knew, and there was kind of for obvious calculations, that this can only hold if the characteristic of K is not too small. It should be bigger than the so-called Coxeter number. Coxeter number. Okay. Well, anyway, let me now say something about the history of this conjecture. So, what is interesting here is that we have to think of G as a group scheme. So we have to kind of allow to vary the field K. We fix the group like GLN, but we put in different fields. And as long as the characteristic of K is strictly bigger than the Coxeter number, this should hold. So the history of this conjecture is the following. So the first result there is that this formula holds true if the characteristic of K is big enough with respect to the group scheme. Is big enough. This is an amazing amount of work to prove this. And there were several authors involved. So, for example, Kashtan and Lustig. Kashiwara and Tanisaki. So each of these authors proved a certain step in the overall proof. And then finally Andersen, Janssen and Zörgel. And I have to say, each step in this proof is highly complicated.
So this beginner is only dependent on the group G?
Yeah. You fix the group scheme, and then these authors could prove that there is a number n, such that the formula holds if the characteristic of K is bigger than n. But they couldn't prove that this n is a Coxeter number. So the Coxeter number, I should say, in the case of GLN is n. So it's very easy to calculate, and we have a complete list of these Coxeter numbers. So generically this is true. But still, I mean, from a practical viewpoint, this is certainly not convincing, because for any single group, you didn't know if it was true. I mean, there were... No, it's not. The precise bound is not known. Even for, I mean, GL7 or so, it's not known. That was around. So that was in the early 90s, and this conjecture was from 81. So in the early 90s, so actually Lustig, he had a program to prove this conjecture, and this program was then carried out by these authors. It is highly involved. So what goes into this proof is the representation theory of affine Kac-Moody algebras, perverse sheaves on affine flag varieties, quantum groups, the Cauchy-Lustig equivalence between positive level representations of the affine Kac-Moody algebra and quantum group representations, and then an independence of P result of Anderson, Jensen, and Zergel. Finally, we had this statement, but at that time they didn't know anything about the bound. So in around 2007, so I could kind of simplify this proof. So I only needed the Anderson, Jensen, Zergel result, AJS. So, but not the Cauchy-Lustig and Kashiwara-Tanizaki input. It's kind of a simpler result. So first it was the same result, but a simpler proof. But I could prove two more things. So I could calculate an actual bound. So an actual bound on the exceptions. So on the exceptional characteristics. And I could prove the multiplicity 1 case for all relevant characteristics. So so this actual bound, I should say, is very far from the Coxeter number. It is actually a formula in terms of the underlying root system. I calculated it once explicitly for the GL8, and the bound I have. So remember, the bound Lustig gave is 8, would be 8. So it says it should hold for each prime number above 8, and my bound has about 40 digits. 40. So it's really not not even close to the Coxeter number, and also it grows exponentially with n. If so, it's something, it grows something like n factorial to the n factorial, or in this range. It's huge. Yeah, it's something like h factorial to the h factorial or so. So, and this multiplicity 1 case is actually a full proof in all relevant cases of a multiplicity reformulation of this conjecture. So in order to state this, you have to translate this conjecture into an equivalent conjecture not involving the group, but its Lie algebra. And then the standard module, so the replacement of these H0s for the Lie algebra are called baby-Wörmer modules. And the question was about, you can translate this into an equivalent question about the Jordan-Hölder multiplicities of baby-Wörmer modules. And I showed that this is 1 if and only if Lustig's conjecture predicts it to be 1. And this holds for all characteristics above the Coxeter number. So at that time in 2007, that was maybe the strongest result that actually was valid for every characteristic above the Coxeter number. And it was also a hint that maybe the Coxeter number is the right bound. 3 months ago, Jordi Williamson found a counterexample. Jordi Williamson. He's another student of Wolfgang Sörgel. He was doing his PhD in Freiburg when I was an assistant there with Wolfgang Sörgel. He's now a postdoc at the MPE in Bonn. And in June this year, he found not only one counterexample, but a machinery to produce counterexamples. So that is the latest development. So that was June 2013, counterexamples by Jordi Williamson. So it's an infinite series of counterexamples, and so it was of course it was very surprising to find one counterexample above the Coxeter number, but his counterexamples strongly suggest that the real bound is not a Coxeter number or not twice a Coxeter number, but it grows exponentially with the Coxeter number. So the situation is much more complicated than we anticipated. Okay.
What is multiplicity 1?
Oh, multiplicity 1 is the following. So you translate this into a Jordan-Hölder multiplicity conjecture for baby Wörmer modules for the Lie algebra of G. And then this conjecture so I proved that that a simple module for the Lie algebra appears in a baby Wörmer module with multiplicity 1, if and only if it's predicted to do so by Lussig's conjecture. So that's multiplicity 1 result. So, I mean, this doesn't occur so very often, the multiplicity 1 result, but that's the only thing that's actually valid for all relevant characteristics. And for multiplicity 2 or 3 or so, it's probably not true anymore. So we have these counterexamples. So let me now talk about the
What was the motivation
method?
to the Coxeter number as a bound?
That's a good question. So, I can say two. So, yeah, okay. So let's say it's pure optimism.
Lambda alpha is positive for all positive, less than B. For all positive, it's not simple rules.
Yeah, exactly. Here it is for all positive roots. But then you apply elements of the affine Y group and you end up with all restricted highest weights. So it's this is not this doesn't satisfy the stronger condition, but it's still restricted. So, but back to your question. So first, it's pure optimism because it is absolutely clear that everything then generates heavily once the characteristic is smaller than the Coxeter number, and this. The reason for this is the following. So you see the affine Y group appearing. So So X is an integral lattice, and the highest weights that we are considering are the integral points. Here is there. I guess there's a point here. Are the integral points inside this this dominant Weil chamber? And already in the SL2 situation, so this is the picture for GL3, or rather SL3 maybe, SL3, and already in GL2 or SL2, that's kind of it's the same complexity. we have seen that, so it's one-dimensional, and we have seen that as soon, we have this Ln at integral points n, and as soon as we reach P, there's the Frobenius action producing submodules, and so this suggests that here so something happens once you translate these hyperplanes by P. So once you translate these hyperplanes by P, there might be something happening in the SL2 direction, in the corresponding SL2 direction, and the reflection group in this affine setting is the affine Weyl group, and if the characteristic, if P is smaller than the Coxeter number, then these hyperplanes are such that there's no integral point in the inside of an alcove anymore. So, so that is an alcove, and in order to formulate Lustig's conjecture, you need an integral point in the alcove, and there's just no alcove. So there's no hope that the formula makes any sense. So when Lustig stated his conjecture, it was known that it's the most optimistic guess because everything breaks down once the characteristic is smaller than the Coxeter number. And then he wrote in his article that the evidence for his conjecture is very strong, and he lists sample calculations of Janssen, but they are rank 2, rank 3 cases. And I think he might have had some doubts once he published his conjecture, because he never mentioned the Coxeter number again in any paper afterwards. For a good reason that we know now.
You don't have, but there is no complete reducibility statement for the Weyl module. Is it beyond the Coxeter number?
Say it again. This?
The Weyl module.
Yes.
Is it?
Oh yeah. There's okay. Okay. So once you are below the Coxeter number, you only have singular situations, and you know which Y modules are irreducible and which aren't. But you don't have a general statement about those, and there's not even a conjecture. So no one really knows what happens once the prime is small. But for very small Y modules, for very tiny lambda, you can say, okay, it's irreducible, it coincides with L lambda. I think it's the case if it's still, if it's still on one of the walls of this fundamental alcove. Okay. So now, So let me talk about the approach to this problem. So there's no way to attack this problem using pure representation theory. So far, you have to translate it into other theories, and one possibility is to relate it to sheaf theory on an affine Grassmannian, and this goes as follows. So this is a completely new setup now. We define GR, the affine Grassmannian associated to G. So this is the following. So you take your group scheme G, and you plug in the quotient field of the ring of polynomials in one variable, and you divide. Yeah, okay. Let's say you divide the ring of Laurent, the entries in G are in a ring of Laurent polynomials, and this is the affine Grassmannian, and this is a complex int variety. It's a kind of infinite dimensional space, but it's filtered by complex finite dimensional projective varieties. So you can talk about the topology and the sheaf theory. Everything we write down will be supported on one of these finite dimensional projective varieties. So we don't have to worry about infinite dimensional phenomena here. This is the affine Grassmannian. And we consider this as a topological space using the metric topology on these finite dimensional projective varieties, and we obtain an equivariant. So we obtain the derived category of sheaves on of k vector spaces on this complex variety, and we should consider them equivariantly. Well, let me just to don't get it too technical. Let me forget about the equivariance condition. So what is that? It's a derived category of sheaves of k vector spaces. So our K, our field of, our defining base field for the group, here appears as field of coefficients for sheaves on this topological space, but the variety is still a complex variety. And now there's a definition. So an object here. Maybe I should say that this is a stratified space. So it's acted upon by a subgroup, which is the Iwahori, a subgroup of this loop group, which is called the Iwahori subgroup. So the Iwahori subgroup, it's contained inside this disk group. It's also an infinite dimensional subgroup, and so GR is stratified by these orbits. And so let me, before I give the definition, let me write down some facts. Okay, so so if so GR, this is a kind of generalized Breuer decomposition, is stratified by I orbits. So I x G C T modulo G C T, and x is a dominant weight. So here we have a kind of a Breuer decomposition, and this let's call this CX. Let's call this CX. Anyway, it's a stratified invariety, and now we define parity sheaves.
This is all time.
Pardon me?
These are each of it is.
Yeah. So yes, this is right. So this is a Schubert cell, and the closures of those are the partial Schubert varieties in this kind of partial Fleck variety setting, and the dimension is x evaluated at rho on, I mean, so this is these are affine spaces.
So this the John Dewey is over the cells, dominant characters of.
Right, dominant characters of the dual group. Right. So I mean, if I should be very honest, of course, and I should put the check actually here. So there's some kind of duality between roots and co-roots going on here, but okay. So F is an element in this derived category is called even if the following condition holds. So if the pullback on this Schubert cell corresponding to X, so Ix is just the inclusion of this stratum, if the pullback of this sheaf is a direct sum of constant sheaves shifted by even degrees. I mean, every element in the derived category can be represented by a complex. And what I'm saying here, it's a direct sum of trivial complexes that only have an entry at one point in even degrees. And it's a direct sum of these complexes. It's a direct sum of constant sheaves shifted by even degrees. It's odd. Well, you can imagine if the shift by one is even, and its parity. It's a parity sheaf if f can be written as f0 and f1, where f0 is even and f1 is odd. So it's kind of simple to write down this condition, and so, yeah?
Does this essentially say that it's a formal, that it's isomorphic to a formal complex with zero differentials?
Yeah, but only the pullbacks on not the sheaf as a whole, but only on these affine spaces. Yeah. Or Cx. Yeah, you restrict it to one of the stratums, and then it should have this parity vanishing property. So now, these parity vanishing properties, they allow to kind of formally prove some very nice results. For example, a theorem of so this definition goes back to Juteau, Daniel Juteau, Karl Mautner, and Jordi Williamson, and they also proved, Juteau, Mautner, Williamson, there is a unique indecomposable parity sheaf I guess they call it EW, with the following property. So it's indecomposable. The support of EW is contained in the closure of the corresponding stratum, and if you restrict it to the biggest stratum, to the open stratum in this variety, then this is just K, the constant sheaf in degree 0. And each other parity sheaf is just a direct sum of shifted copies of those. This holds in a much more general situation, but you have to replace this uniqueness property by saying that there's at most one. So in many situations, it's not clear that these sheaves, but in all flag variety settings, you can prove that these sheaves exist, and then they are unique. So We have,
W is an X plus. Some of random.
yeah, so this is, yeah. But you can do it on every partial flag variety. So, right, maybe, I mean, so I haven't, so I'm not very precise here. I mean, yeah, let me ignore some technical details corresponding to the fact whether, we choose a simply connected group or a joint group in this situation. Well, let me ignore this for the moment. Back to representation theory. So you prove that Lustig's conjecture, as I said, is equivalent to a multiplicity conjecture. And this multiplicity conjecture is as follows. So by G, we denote the Lie algebra of this group. So this is a modular Lie algebra over the field K of positive characteristic. And then you define a certain subcategory in the category of G modules that carry an additional X grading. So these are X graded G modules. So this is a Harishchandra subcategory. So it's defined as follows. So an object here should be a G module, which is graded as a vector space by the set X. So the set X are the characters of the maximal torus. So on each graded component, homogeneous component, you have an action of the torus given by the corresponding element, and you want that the action of the Lie algebra in G is the derivative of the action of the torus on this one component. So it's a kind of Harishchandra category. Category C, and then for each lambda in X, you define the baby-Böhmer module. Set C lambda in C is what is called the baby-Böhmer module. And this is a kind of highest weight category. So it has a unique simple quotient. So now we call this LC lambda. It's not the same, or it's not the derivative of L lambda in general. So ZC lambda to LC lambda is the unique irreducible quotient. And then Lustig's conjecture is equivalent to the following conjecture. If lambda is antidominant for the finite Weil group and regular, antidominant for the finite Weil group and regular, then the Jordan-Hölder multiplicity of this baby-Böhmer module should be given by another polynomial evaluated at 1, and this is the so-called periodic Lustig polynomial. That's just another Kashtan-Lustig type polynomial. Anyway, so you prove that this is the multiplicity statement I was talking about earlier. So now let me connect the two theories. You see, here we have the parity sheaves. Here we have the multiplicity conjecture, and so
Positive number also.
Yeah. Same restriction, yeah. If I mean, I shouldn't write this as a conjecture anymore because it's not true. But the hope was, so the original Lucid conjecture had the same assumption on the characteristic. That was equivalent to this conjecture also for a characteristic bigger than the Coxeter number. One more step before I can give you the central result. One more step, and this is Humphrey's reciprocity, which is a version of an earlier version of the BGG, Bernstein-Gelfand reciprocity for category O. It says that LC lambda admits a projective cover, QC lambda in this category C, and QC lambda admits a baby Wörmer flag that is a filtration by sub-objects such that each successive quotient is isomorphic to one of the baby Wörmer modules. And the reciprocity says that the corresponding multiplicity, so if you choose one of these flags and calculate the multiplicity of this baby Wörmer module in the flag, then this is the same as the Jordan-Holder multiplicity of the corresponding baby Wörmer module. So this is Humphrey's reciprocity. Now, you see, we then translated Lustig's conjecture into a multiplicity conjecture for these projectives. Now, finally, I can write down the theorem. So this is from 2007. There's a functor phi from parity sheaves on the affine Grassmannian to the category C. This is Harish-Chandra category of G modules, Lie G modules, from parity sheaves to this category, such that phi of EW is projective, and so this lands inside the projective objects there. So these are the indecomposables here. So it is actually inside the category of direct sum of these Q's. Yeah, it's EW is the unique parity sheaf with this support condition. And this is projective, and the important thing is that so this projective will have a flag, and phi of EW, if you want to know how often that x dot lambda appears in a Wörmer flag of this projective, this is the same as the dimension, say, of the local cohomology of EW at when you just pull it back on the stratum. So what does that say? You have this parity sheaf and addition theory to the geometry of the affine Grassmannian. And now, as a final step to, this means now we have to study these parity sheaves, and if
Suppose there is no characteristic eventually.
Yeah, this is, yeah, but so if, yeah, so this is, it's so I mean, morally it's if the characteristic of K is bigger than the Coxeter number. I mean, there's an assumption depending on W. But we need only finitely many W's to approach this character problem. And for these finitely many, if you restrict this to these finitely many W's, then the characteristic must be bigger than the Coxeter number. Again, but no further assumption. So we have to study these parity sheaves. If the characteristic of K is 0, then the decomposition theorem in algebraic geometry implies that EW is the same as the intersection cohomology complex on CW bar with K coefficients. And this is now a characteristic 0 statement. This is an intersection cohomology sheaf, and this then implies with some combinatorics that the dimension of this local cohomology Ix upper star EW is given by an affine Castanistic polynomial. This is known. And now you see we get the connection. So the conjecture here was that this is given by a by a periodic polynomial. But funny, I mean, it's quite funny that in the relevant cases, this polynomial is not the same as the polynomial appearing here, but if you evaluate it at 1, it's the same. It's very, very strange. Anyway, using all these identifications, you know this dimension. This is the corresponding Baby-Wörmer multiplicity. This is the Jordan-Hölder multiplicity. This gives Lustig's conjecture at the end. In characteristic, I mean, this is still in characteristic 0, but once you know it in characteristic 0, because this is a kind of finite, it has a kind of algebraic core, you can argue that it's also true for P big enough. I mean, in the construction of IC complexes, only finitely many rational numbers can occur, and you have to exclude the prime divisors of the, yeah. And so this is true for P big enough, and the finer study yields the upper bound. Yeah. So this is the overview of the approach towards Lustig's conjecture using parity sheaves on affine Grassmannians.
This is what you were saying, your approach.
Yes, I mean, so yeah, this is a theorem I proved, but I have to say that there's an earlier theorem due to Wolfgang Zörgel, which doesn't use the affine Grassmannian but the finite dimensional Fleck manifold. It has a similar result, but it captures not all of Lustig's conjecture, but only a finite part of Lustig's conjecture. And this is also, I mean, the underlying philosophy is what I would like to call Zörgel localization. So it's a kind of motivated by Zörgel's approach to representation theory. But it's, I mean, it's in the affine situation, and it captures the whole of Lustig's conjecture. But it has some predecessors. Okay. Thank you very much.
Are there any questions?
For the modification, there is no problem because you are equivalent to the strict and the Coxeter number. And that creates no problem when you do this equivalence finally.
You mean this is true for each characteristic above the Coxeter number? This is true for each. So this is only assumes the characteristic to be bigger than the Coxeter number. This is always true. But For small characteristics, we don't know this dimension. So we know this dimension in case our ground field is of characteristic 0, because then it's an IC complex and we know everything. And then we can already deduce that there's an upper bound on the exceptional characteristic. So it's almost always true. But from so far, we cannot, for each given prime, we cannot say, I mean, if it's an exception or not. From what I told you here, there's no way to deduce the exceptional primes. You need some finer study of this to give an upper bound on the exceptions. But it comes from this theory.
So even here it becomes like an exponential in box interval.
Yeah.
Even for this? Well, this seems to be the multiplicity side of the
Right. Already. So right. Already. So here you ask the question. Okay. This is the essential. This is the essential identification, and you can ask for which K is the parity sheaf and intersection cohomology complex. And so let me think. Jordi Williamson produced his counterexamples not topologically, not in this setup, but in the setup of Sergel bimodules, which I haven't introduced here. But there's, so let me see, I think it's an equivalent statement. I think you can deduce that for his counterexamples also this identification fails. Yeah, right. Otherwise, would yeah, this implies Lussig's conjecture.
Any other questions? Let's stand and speak once again.